Perfect. He did.
Yes, sir.
Okay. So welcome everyone for this ICWaR seminar for the month of April. And we're very glad to have Professor Mal Macmillan from Lancaster University as our speaker. He's a co-director of science for the UK Centre for Polar Observation and Modelling and a co-director for the joint Lancaster University UK CEH Centre for Excellence in Environmental Data Science. And Mal is a very well-known figure and I think one of the foremost scientists you can think of when it comes to ice sheets, right? The two caps, the polar caps of our planet. But it's not only that. I think his understanding of the cryosphere and how it is responding to climate change is obviously up there. And it is a pleasure for us to have him as our speaker. And we look forward to his talk, which is about monitoring the Earth's ice sheets from space, some remote sensing component. And I'm pretty sure there will be many questions, many questions would arise in your mind while listening to the talk out of curiosity. And also, maybe genuinely you wanted to understand a few more things in detail. So I request you to kindly not interrupt in between the talk. Once the speaker is done with the talk, you can raise your hand and unmute yourself and ask your questions. Also, whoever joins, please keep yourself mute. And during the whole talk, it would be nice if only Mal is speaking or Mal's microphone is on. Yeah. So, Professor Mal, the floor is yours. And again, thanks a lot for joining us today for this interesting talk.
Thanks very much, Brahma. So yeah, thanks very much firstly for the invite for today. It's a pleasure to come speak to you today, and thanks all for turning up to listen. So as Brahma says, I'll talk to you today a bit about work that we do to map Earth's ice sheets from space. So this is mapping elevation and mass changes over the Greenland and Antarctic ice sheets, primarily using satellite observations. So I say we, but I want to start really by, I guess, acknowledging the team that we have in Lancaster within our group. So although I will present the results, all the results are really down to the hard work of these group of individuals, and these are both past and present members of our group. I particularly wanted to give a shout out to Maya, who was the first postdoc that we had here in Lancaster, and is responsible for me coming to talk to you today. So thank you, Maya, for that. Okay, so in terms of the scope of the talk, so I'm aware that it's a fairly broad audience, and so I won't go too much into kind of technical details, although I'm very happy to answer questions on that at the end. But instead, I'll try to give you a broad overview of some of the kind of the glaciological and the climate and the physics related questions that we work on within our group, with the kind of the broad connecting theme that we use. In all cases, we use satellite data to try and understand them. So in terms of the talk, I'll start with a bit of introduction in terms of what we're measuring and why. Then I'll talk briefly about quantifying contribution of ice sheets to sea level rise, and how we use satellite datasets to do that. I'll then talk a bit about a few different examples of how we use the satellite observations to study the physical processes that are actually driving those changes through the atmosphere and ocean interactions with ice sheets. And then I'll finish just with a couple of thoughts in terms of some of the future directions for work. Okay, I always kind of like to start with a video because I may be biased, but I think the cryosphere is one of the most beautiful parts of our planet. So obviously, as kind of glaciological or glaciology scientists, we're interested in understanding how ice on Earth is evolving through time. And this is really, I guess, a really important question currently with the kind of unprecedented changes that we're seeing within the polar regions, both in terms of Earth's atmospheric climate and also the oceanic climate. And the way that ice sheets and ice caps and glaciers respond to that through their melting and through their dynamical and thermodynamical changes ultimately impacts upon us all in terms of rising sea levels, changes in the climate that we feel. And so it's really important that we both monitor these changes as they're happening, and we understand the processes driving these changes, so that we can make accurate predictions or projections or forecasts going forward in time. So from satellite observations, we know that the global mean sea level currently is rising at about between 3 and 3.5 millimeters per year. This represents an increase through time, and a significant contribution of this global sea level rise is due to melting of Earth's ice sheets and also mountain glaciers, with the rest coming from thermal expansion of the oceans and also changes in groundwater storage. So what drives these changes? What drives the changes in the polar regions and the ice sheet? Well, there are kind of a number of kind of broad strands. So first, I guess most simply, there's atmospheric warming. So as Earth's atmosphere warms, then that obviously drives increased melt at the surface. So we know that global mean temperatures are warming, but we also know that through the process of Arctic amplification, that the Arctic is warming at somewhere between 2 and 4 times faster than the global mean. And so this means that there is a stronger or more extreme impact in the polar regions, particularly in the Arctic. Alongside kind of this long-term trend in temperatures, we also know that there's changes in atmospheric circulation. So we hear a lot about extreme events in terms of how that can impact upon the ice sheets, in terms of atmospheric rivers driving kind of intense warm periods over ice sheets. And so understanding how atmospheric circulation impacts upon the ice sheets is important. And then thirdly, there's the impact of the ocean. So where the ocean melts or interacts with the ice sheets, then any changes in the ocean temperatures or the circulation have the impact to, or have the capacity to make changes to the ice sheets. So we can use satellite observations to measure changes in ice sheet mass and hence their sea level contribution back to the early 1990s now, which is when we started to have routine observations. So these are data sets from the ice sheet mass balance into comparison exercise, which is a large scale kind of study of how ice sheets have changed. And we see that over that broadly 30-year period, there's been a roughly 6-fold increase in the contribution that ice sheets are making to sea level rise. Greenland is contributing slightly more than Antarctica, but arguably Antarctica going forward is more uncertain in terms of how it may respond in the future. And so these observations are important for quantifying the current sea level rise from ice sheets, but they can also be used then to constrain or to compare to future projections. So in these two plots, we have on the left plots for Antarctica and on the right plots for Greenland. In each case, the blue line is the observational record, so the record we have from satellites of how ice sheets are contributing to sea level. And then the colored curve shows projections, so numerical model future projections from the IPCC of potential kind of future pathways of what we might expect. And so we can see that in both cases, current observations are tracking closest to kind of the upper pathway within these studies. And so these observational records are really important because they allow us to be able to compare and test to projections and how we might expect climate to evolve in the future. So what actually impacts upon ice sheets? What are the interactions that drive changes in the ice sheets? So as will be no surprise, it's a complex picture. So we have interactions on the surface of the ice sheets between the atmosphere and the surface. We broadly refer to these as surface mass balance processes. So these can be things like accumulation from snowfall, ablation, so melting from warm temperatures, and then associated kind of features such as surface hydrological systems that form on the surface of the ice sheet. Then for marine terminating ice sheets, so parts of the ice sheet that terminate in the ocean, we also have a number of other processes related to how the ice sheet interacts with the surrounding ocean. So we have carving dynamics, so how icebergs carve off into the ocean and are lost from the ice sheet. We can have basal or frontal melting, so where we have ice cliffs, ice tongues, or ice shelves, then we get melting underneath and on the lateral extents from them. And so understanding how those melt rates evolve through time is important for understanding how the ice sheet might respond. And then we also have subglacial hydrology, which is how the movement and storage of water at the base of the ice sheet. And I'll look throughout the talk at a few examples of how we can use satellite observations to understand some of these processes. So how do we track ice sheet mass loss? So broadly speaking, there are three different techniques, three different satellite techniques for doing so. There's altimetry, there's gravimetry, and mass budget, which is sometimes referred to as the input-output method. And so the pie charts at the top here show from the community assessment the kind of the relative distribution of those different techniques that are used. And then in the bottom plot, you see kind of the time scale over which we have observations. So my work and the work of our group primarily focuses on the technique of radar altimetry, which has a continuous record back to the early 1990s. We also do a bit of work with laser altimetry, but less so. So I said I won't give too many technical details, but just a very brief explainer. So altimetry works by essentially firing a pulse of electromagnetic radiation and then recording the time it takes to reflect back from the surface. And that allows us to get a measure of the elevation of the ice sheet surface at any particular point in time. So this is just an animation of kind of a visualization of what the altimeter is measuring. So in the top, you kind of have a 3D view of what the altimeter is measuring in terms of the purple footprint that's illuminating the ice sheet surface below. Then in the bottom left, you have the actual data that's recorded by the satellite. So in this case, we refer to it as a waveform, and it's basically a histogram of the power that's received by the satellite. And then in the bottom right, you kind of have a slice through the topographic profile that's being measured, with the purple showing the surface topography and the green box showing essentially the area that the altimeter is tracking. And so as the satellite flies along, we record these sequence of waveforms, and from them we estimate the surface elevation of the ice sheet. And then what we can do is we can track how that surface of elevation evolves through time as the satellite acquires measurements over the ice sheet. So here we have measurements of surface elevation as the satellite orbits over the Antarctic ice sheet. And then we can build that up through time to get a complete picture. And then as we repeat those measurements, we can detect areas of the ice sheet that are rising, where the ice or snow is being gained, and regions where it is being lost. And that allows us to estimate mass balance. So we do that with a range of different satellites dating back to the early 1990s with the launch of IRS-1, through to kind of current satellites, which are CryoSat-2 and Sentinel-3. And then we're looking forward to the launch of the next radar altimeter, CRISTAL, hopefully towards the back end of next year. And so these measurements allow us to build up quite detailed pictures of how the surface of the ice sheets is evolving through time. So on the top, we have Antarctica, on the bottom, we have Greenland. Essentially, everywhere that's red is where the surface is lowering through time. And so we're seeing loss of ice. And then blue, conversely, we're seeing gains in ice. And we can track that through time for different regions of the ice sheet. And this allows us to understand areas of the ice sheet which are gaining mass and areas which are losing mass. So in summary, if we look at the whole of Antarctica, we see, and we split it into 3 regions. So we have the broad East Antarctic ice sheet in yellowy orange, West Antarctica in blue, and the Antarctic Peninsula in green, and then the total mass change from the ice sheet in black. And so what you can see from the curves on the right, that firstly, Antarctica is losing mass, as we all know. But secondly, that this is primarily driven by changes in West Antarctica. To a much lesser extent, we also see changes on the peninsula, and we see modest gains in mass in East Antarctica due to snowfall. If we split that out a bit more, then we can isolate kind of the key regions or the key glaciological basins that are kind of currently responsible for a large part of Antarctica's imbalance. And these are given in the top plot in blue and yellow as a proportion or relative to the total West Antarctic change, which is given in black. And these are the basins of Pine Island Glacier and Thwaites Glacier, which drain into the Edmonton Sea in West Antarctica. And these make up around 84% of the total mass loss since, I guess, the early 1990s. In East Antarctica, we see a more variable signal. So we do see some regions that are also losing mass, most notably the Totten Basin in East Antarctica, which is the green basin, the green curve. But we also see a lot that this is largely offset by mass gains in a number of other basins where we're seeing kind of higher accumulations of snowfall. So I hope that gives you a bit of a flavor in terms of how we quantify kind of mass loss or mass gain from the ice sheets and what it tells us about the current state of them. In the next part of the talk, I wanted to discuss in a bit more detail about how we can actually use the satellite observations to resolve the environmental processes that are driving the changes that we see. So I'm thinking here about changes in the atmosphere, changes in the ocean, and how these drive changes in the ice sheet. So I'll go fairly quickly, but I thought I'd give kind of 4 different case studies. So I'll firstly talk about surface mass balance processes, so processes that happen at the surface of the ice sheet, and some work we've been doing there to try and quantify that using altimetry measurements. I'll then talk a bit about how we map grounding lines, and then I'll look at a couple of other examples. So the first 2, I guess, rely on altimetry data, so the kind of data sets that I suppose are kind of the bread and butter of what our group uses. But then the second 2 actually utilize other Earth observation data sets. And so I thought I'd give a couple of other examples of some of the kind of the other EO-based data sets that we're currently working on. So if I start first with surface mass balance processes, so why are we interested in looking at these? So I guess it's pretty clear that as Earth's climate warms, the melting and the runoff of meltwater from the ice sheet will accelerate. And we know that the kind of particularly for Greenland up to 2100, that sea level rise from this runoff or from these surface mass balance processes will accelerate throughout the century. And it's also kind of highly sensitive to the forcing scenario that's taken. So, but we have some challenges here in terms of monitoring it. So there's a number of ways that we can monitor runoff. So we can monitor it from kind of in situ field campaigns. But I suppose they are because of the logistical kind of difficulty of deploying and maintaining them, they tend to be relatively sparse in space and time and difficult to maintain. We can use numerical models, so climate models, but we have to be aware that these are obviously not observations, and so whilst they're important for making future projections, they don't actually give us observational data sets of the current state. And this is particularly important because we know that current models typically can underestimate extreme events by quite a significant magnitude. So we have current satellite techniques that can measure the extent of melt on the surface, and I'll look at one of these in a bit more detail later on, but they don't actually quantify the volume of meltwater that's generated. And so what we wanted to look at here is whether we could use our altimetry measurements in a bit of a different way to try and quantify these meltwater volumes. So what does that mean in practice? Well, as I've shown, what we can get from our altimetry records is a record of how the surface of the ice sheet changes through time. So here you can see a record over the whole of the Greenland kind of ice margin of how the ice sheet has changed in elevation through time. And when I introduced the mass balance studies that we did earlier, then essentially what we're looking at is the long-term trend here. So what is the decadal trend in elevation change through time? And how does that equate to a change in ice mass? So within this work, what we wanted to do instead was focus on these seasonal changes. So these seasonal cycles, which are essentially associated with ablation of the ice surface during summer. So it's how much the surface lowers during summer due to that summertime melting. And so by looking at those shorter term changes, we could use this to estimate rates of ablation over the ice sheet, which then we can convert into an estimate of the surface runoff that's occurring. So when we compared this to in situ measurements, we saw that we were able to achieve a relatively good or strong agreement in terms of the strength of the correlation between the two data sets. So showing that our approaches for estimating ablation rates agreed relatively well on an annual basis with those from in situ data. We could also compare them to climate model simulations, and this, I guess, gives us confidence in both data sets. It's not a direct validation or accuracy assessment, but the fact that we see quite strong consistency in terms of those interannual variations gives us, I guess, confidence that they're both resolving similar signals. So what this allowed us to do was to essentially quantify for the first time runoff over the Greenland ice sheet through time over the past decade. So we estimated that around 360 billion tons of water ran off into the ocean each of those years, and that was represented likely around a 20% increase compared to what had been observed over the past 3 decades. And not only did we find that magnitude had increased, but we also found that we were seeing higher year-to-year variability. So in effect, annual changes were becoming more variable through time as Earth's climate warmed. And so this is something that we're looking to extend to other satellite missions to really try and essentially operationalize what was an R&D study and to routinely produce these observations. So the second kind of process that I wanted to touch upon was that of grounding lines. So this is work that Maya and I started when she was in Lancaster, and we continue to work on when we have time. So grounding lines are important in Antarctica because essentially they tell us where regions that are stable, regions that are retreating in Antarctica. So a grounding line is essentially where the ice detaches from the bedrock underneath and starts to float. So you can think of it as an estimate of essentially the lateral extent, and where that is retreating through time, it suggests that we have an imbalance. And so again, here we were interested in how we could use radar altimetry in a novel way that went beyond just mass balance studies to actually try and track and map this this kind of key parameter. And for this, we focused on using the Sentinel-3 satellite because I guess it has a number of benefits. So it's a SAR altimeter, which essentially gives us higher resolution. But I guess crucially, it's an operational monitoring program. And so we know that we will have long-term continuity of these measurements for decades because of the program that it operates in. And so this was really a proof of concept to look at, well, what could this form the basis of kind of a future operational system? And so we focused on a test site in the on Filchner-Ronne ice shelf Antarctica. So this is a specific ground track that you can see in color, and a specific area close to the grounding line. And essentially, what we can do is we can look at profiles across the grounding line of elevation. And what you can see here is one from each kind of cycle, so each month when the satellite acquires data. And what you see is that when you're on the floating ice shelf, you see a larger vertical spread or dispersion in those profiles. And that's due to the fact that the ice is floating, and so that it moves up and down with the tides and with changes in atmospheric pressure. Whereas on grounded ice, you get a much more stable signal. And so what we showed, or what Maya showed, was that by using these measurements, we could actually look to fit a model to these measurements and then pick out a point where the grounding line was. So you can see some examples here of fitting model to these data sets. And then what that gives us ultimately is an estimate of the grounding line position, which is within around 100 meters of that derived from independent data sets. And so this is something that is really encouraging in terms of developing a new application for this technique, and something that we'll look to or we would like to develop further in the future. Okay, so that's a couple of examples, I guess, from altimetry in terms of the kind of parameters. As I mentioned before, I also wanted to touch on a couple of examples that use non-altimetry data sets. So firstly, I'll touch on mapping surface lakes or surface hydrology using optical data. And so we really now have a wealth of satellite optical data available to us. So the animation on the left really just shows a time series of data required from Sentinel-2, which is an optical satellite, over a region in the northeast of Greenland. So you can see lots of clouds because it's optical data, but you can also see that when there aren't clouds through the summer season, you get formation of lakes on the ice sheet surface as water ponds, and you can also see streams and other hydrological features. And so mapping kind of the surface hydrological system is important because it tells us about how water is stored on the surface of the ice sheet, and also how it moves across the surface of the ice sheet through time over the summer. Lakes themselves are important because they alter the albedo of the ice sheet surface. And also we know that they quite extensively drain through the ice, and that can drive changes in the flow of ice, so the speed at which it flows towards the coast. And also where these lakes form on ice shelves, it can have impacts in terms of the structural integrity of the ice shelves and their capacity or their potential to collapse through time. So I won't go into this in detail, but essentially this is, I guess, what we would class a big data challenge. So the ice sheets are large. We have these data sets at the scale of kind of 10-meter resolution, and we have thousands of images or tiles that are acquired every year across both ice sheets. So we end up with kind of hundreds of terabytes of data, hundreds of thousands, up to millions now of useful tiles of data. And we want to really use all of these data, these valuable data that have been collected, to try and extract as much information about surface hydrology as we can. And so I suppose this is kind of a common theme across satellite observation at the present, is then obviously this is a data challenge. And so looking at how we can use machine learning, deep learning approaches to automate and scale these type of approaches. So in this study, we've been looking at applying a relatively simple machine learning classifier, so a random forest classification scheme. But what it allows us to do is to kind of to classify or identify hydrological features at scale. So you can see here an example on the left of a surface lake, and then on the right, the classification. So in red, every pixel that's been classified as surface water from this lake. You can see that it also does what should we say, less well at estimating streams. So once you start to go to the resolution of streams that are closer to the resolution of the instrument itself, then you get a more patchy performance. And so currently we're looking at whether we can use improved approaches to enhance it. But we are able to pick out some information about where stream networks are. And that's just a third example. And so what this allows us to do then is to really scale this up to large scale. So essentially to try and generate monthly maps over the whole of the ice sheet in terms of the hydrological system. And this really, I guess, gives us a wealth of information, which we're still really analysing to try and understand fully in terms of how Greenland's hydrology evolves through space and through time. And this is really important, I suppose, for giving us kind of, or for fully utilising the wealth of data that we have available to us, but then also understanding how these processes interact upon the ice sheet as a whole. Okay, and then fourthly, I just wanted to touch upon subglacial lakes. So subglacial lakes are lakes that form beneath ice sheets, so at the interface between the ice and the underlying bedrock. And so in Antarctica, we have a pretty good handle on the distribution of lakes. So far, around 700 lakes have been mapped beneath the ice sheet. And many of these are mapped using EO or Earth observation techniques. So specifically active lakes where the surface is either going up or active lakes. So these are lakes where water is being gained or lost from these lakes. And when that happens, we see a signature on the ice surface that we can track. So this is one example of a lake called the Cookie 2 Lake in East Antarctica. And what we see when we use the altimetry to map the surface above this lake is we see a very large depression in the ice surface. And this is essentially where the water body under the ice has drained, and then the ice has collapsed on the surface, and this forms a topographic depression. And if we look at how the surface has evolved through time, which you can see in the right-hand plot, you can see that there was a relatively stable ice surface, and then a sudden drainage event where over a period of about 18 months, the ice surface dropped by about 70 or 80 meters. So quite a large event as this lake drained. So I'd say mapping these lakes over Antarctica is relatively mature, and using altimetry to do so is a fairly well-established technique. However, in Greenland, this isn't the case. So this slide is slightly outdated now, but broadly we know that around 100 lakes exist and only 6 active lakes exist. And this is despite kind of numerical predictions, which suggest that there should be kind of order of magnitude more lakes than have actually been discovered. And this is primarily because the altimetry data that we use in Antarctica is not high enough resolution to be able to map the lakes in Greenland. So Greenland is much smaller. We believe that lakes are generally much smaller, and they're kind of beyond the resolution limits that we can conventionally achieve from altimetry. And so kind of a new strand of work that we've been spinning up in the group in recent years is looking at how we can use high resolution digital elevation models to start to get a better handle on the lakes. So this is a 3D representation of the surface that's been derived from the technique of stereophotogrammetry. And what we can do is we can look at how the surface changes through time. And here you can see evidence of where the surface of the ice sheet has kind of collapsed or subsided, which we infer to be from a draining of a subglacial lake. And so the advantage of using these data is really their spatial resolution. So whereas for altimetry, typically we have a resolution of say 100 meters to a kilometer, these are posted at 2 meter resolution. So a really fine resolution that can really provide immense detail over the ice sheet. Again, this provides, I guess, a data challenge when we want to do this at the ice sheet scale, that if we're trying to map the ice sheet, the whole ice sheet, which is hundreds of thousands of kilometers in area at 2-meter resolution, then this can be quite challenging. And so what we've been doing is looking at trying to develop automated approaches to kind of extract information from these data. And what I'll touch upon here is just one example of to kind of give you an idea of how we believe these data are useful in terms of understanding ice sheet processes. So I'll take you to the far north of Greenland. This is a glacier called Harder Glacier, which flows out. It's marine terminating, so it flows from right to left out into a fjord at its margin. And so what we do is we use these digital elevation models. So we stack them through time, and then we look at the variation in the elevation through time. And what this allows us to do is essentially separate out different kind of glaciological signals. And in particular, in this case, we can see this hotspot in yellow, which is where we see a really high standard deviation in the ice sheet surface. So through time, the ice sheet surface is varying by an unusually large amount. And when we look into this in more detail, we can see really large fluctuations in the surface. So we see that in the period 2012 to 2010, we see that the surface is bulging. And then we see around an 80-meter drop in the ice surface by 2015. So a kind of a real collapse in the ice sheet surface. And then we see subsequent uplift of the surface. So it's probably perhaps easier to see if we look at kind of 3D representations of the surface kind of before and after this event. So on the left, we have a digital elevation model from before this event. And then on the right, we have one from after. And you can see how previously the surface was bulging, and then subsequently it's collapsed to form this kind of huge crater in the ice. So this is an area of around 2 kilometers, so something that might have been beyond the scope of kind of our conventional altimeter techniques, but it's really deep, around 80 meters deep. And so we can quantify an estimate of the amount of water that we think has been discharged from this lake, so around 90 million cubic meters of water, and also the discharge rate based on the temporal sampling. So this in itself is interesting, but in this case, what I guess was more interesting was what we observed in the digital elevation models downstream of the lake. So again, we've got 3D representations of this surface feature on the top right from before and on the bottom left from after. And what we see is that before we had kind of a smooth, flat ice surface, and then after the event, we see kind of raised ridges and crevasses and fractures that have formed in the ice sheet surface. Just skip that one. And so what we think has happened here is that actually there's been a subglacial flood from the lake, but this flood has then actually, I'm sorry, I don't know how jerky this animation is for you, so I apologize if it's not very clear. But essentially we see that the lake has drained underneath the ice sheet, but then that water has actually been able to propagate or fracture up through the ice sheet itself and burst out across the surface of the ice sheet. And so we get these fractures in the ice sheet surface where the water has come out at the surface. And then we see a scouring, a sort of clean ice further downstream where the ice surface has been scoured clean. And this is interesting because this isn't a phenomenon that has been observed before in Greenland. Typically, it's always been believed that water has flown out along the base of the ice sheet and not been able to come back up to the surface. And so I guess it raises questions about whether this is an emerging phenomenon and also whether it has any implications in terms of how we model hydrology of the ice sheet in the future. Okay, so I'm conscious of time. I'll just spend a couple of minutes on kind of a couple of kind of future directions that we're working on as a group, and then I'll wrap up. So I just wanted to give a couple of examples of kind of future directions that we're looking to work on going forward. So one in terms of the sensors or the platforms that we're using, and one in terms of the methods that we're using. So in terms of platforms, I guess I focused here on what we use day to day, which is satellite observations, so observations from space. But I think, alongside this, we're also starting to think about other kind of more low carbon platforms that we can use. And so as part of a UK project that we're currently working on, we're thinking about how we can use, or how we can develop solar powered stratospheric gliders that can actually make measurements from the stratosphere, but in a low carbon way. And these, I think, are probably some way off being operationally, but I think will be really a really exciting kind of change in how we actually observe the polar regions in terms of providing persistent monitoring through time. And then the second example I wanted to give was really just on the kind of the machine learning side. So I provided a very simple example of how we kind of use a machine learning classifier to kind of retrieve glaciological information at scale. But we're also thinking, I guess, much more deeply about how we integrate machine learning into our processing workflows, really to exploit the full kind of information potential of all the data that we have available to us. And so on the altimetry side of things, we're thinking about how we actually take our conventional processing schemes and we actually redesign them almost in their entirety to have a more data-driven approach. And because of time, I won't go into the details of this, but essentially what we're looking to do is looking at whether we can train probabilistic neural networks to actually make predictions from the raw data, so from these raw waveforms that I introduced at the start of my talk, to actually go directly to what the topography corresponding to that waveform might be. And so on the top, you have a waveform that the neural network has never seen before. And then on the bottom, you have an estimate of kind of the topography in orange that it believes this waveform originated from, and then in blue, the actual topography. And so I think this is kind of an illustrative example, but how I think that actually data-driven approaches such as this will really probably fundamentally alter how we process data in the future. Okay, so with that, I'll just close with a few thoughts. So I suppose hopefully I've convinced you that within, I guess, the current context of a rapidly changing climate, satellites really are an essential tool for monitoring the impact of climate change upon the polar regions. So more specifically, I think satellites are valuable in two aspects. So firstly, they allow us to quantify the current rates of sea level rise from ice sheets. But secondly, they also allow us to better understand the physical processes, so the environmental processes that are driving change. And that's important for kind of better constraining the numerical models that make future projections of sea level rise, for example. Thirdly, that the systematic kind of long-term monitoring programs are essential. So we need long-term records. So we need programs, satellite programs that last multiple decades to allow us to develop these records. And I think going forward, we need greater emphasis on improving the spatial resolution. So I hope I've shown through the analysis of the digital elevation models how we can get to much more information if we go to finer scale. Robust uncertainty estimation is really critical. I think there's some work to go there. And then ultimately better integrating the observations that we make with physical models in order to kind of bring the two together through kind of data assimilation techniques and stuff. So I'll finish there. I've put a link in the bottom to our UK Centre for Polar Observation and Modelling portal. It actually takes you to the sea ice datasets that we produce currently, because we're doing a bit of a redesign of our land ice portal, but from the same page, soon all our land ice datasets will be available. So if you're interested in any of the datasets that I've produced, then some of them will be available there, and I'm very happy for you to get in touch. Otherwise, if you're interested in any of the others. So with that, I'll finish. I apologize if I've gone slightly over my allotted time, but I'm happy to take questions.
No problem, Mal. No problem at all. Thanks, Mal, for an amazing talk. Now I would request anyone who has any questions, any queries, Please unmute yourself. You can ask, or you can raise hand and then ask. Or if you're unable to ask, let's say you can also put questions in the chat.
Hello, am I audible?
Yep.
Yeah, go ahead.
Yeah. Oh, thank you for the great talk. It's very interesting what you shared, and it was great listening to it. So, could you tell a bit like more about our how important would estimating the grounding lines would be to estimating calving? Will there be relation with that, and how would like from say can grounding lines be also used to help getting better estimates of calving in the ice sheets?
So thanks very much for the question. So the work that we've been doing on grounding lines is focused primarily on Antarctica, and this is where we have like the large floating ice shelves. And so what we're trying to estimate is essentially where the ice shelf starts, so where the grounded ice becomes ungrounded and starts to float. And then I guess so that's kind of at the upstream extent of the ice sheet of the ice shelf, and then at the downstream extent you have the calving front, where, as you say, kind of all the calving processes occur. And so in Antarctica, where we're looking at, there's quite often a large kind of spatial distance between those two, and so they're not, the fact that you saw, say, a grounding line retreat wouldn't necessarily mean that you'd see the same kind of level of retreat of the calving front. But what I would say is that we would expect some kind of relationship between the two. So, for example, a glacier or an ice shelf that's unstable or in a period of retreat, we might expect to see kind of high calving rates, perhaps in the run up to collapse, and also grounding line retreat. And so there's potentially some kind of less direct relationships between the two.
Okay, yeah, okay. So I have another question about like how would be the magnitude of the size and the volume of lakes would compare between Arctic and the Antarctic. So you were mentioning it's much larger in the Antarctic, which would help us to observe it more easily. So could you share a bit more about what are the challenges in monitoring in Greenland?
Yeah, sure. For example, the lake that I showed in Antarctica, right at the start of the subglacial lake section, so that's around 260 square kilometers in size, whereas the lake I showed in Greenland is 2 orders of magnitude smaller than that, so around 2 square kilometers in size. And so what that means is that when we use kind of conventional altimetry measurements, they're pretty good at identifying and tracking lakes in Antarctica, because the resolution of the measurements is much smaller than the size of the lakes. But when we go to Greenland, then those techniques and those data sets tend to struggle, because the resolution is similar or larger than the actual size of the features that we're trying to observe. And so I guess the hypothesis is the fact that we haven't identified that many lakes in Greenland is not necessarily because they don't exist. It would seem strange that they didn't exist, because we know we have a very active hydrological system in Greenland, and we know that water can penetrate from the surface, for example, from meltwater to the bed of the ice sheet fairly readily. But rather the lack of kind of observing these lakes is more kind of an observational deficit, that we don't have the observations to actually be able to observe them. And so that, I guess, raises the question of, well, how can we address that? And so what we've been doing is looking at, okay, well, how can we develop other techniques that rely upon other sources of satellite data which do have higher resolution? And so they have disadvantages. So, for example, they don't provide that regular temporal sampling that the altimetry does. So there's kind of other challenges that are faced with going to using kind of digital elevation models of the sort we use, but we think that they can actually provide us with quite a lot of useful information, which I hope I've demonstrated with kind of the case study that I touched upon. The challenge is really how you roll that out at scale. That, you know, if we're looking at mapping the whole ice sheet at 2 meter resolution and then trying to automate the detection of these kind of features to, say, develop a whole inventory, then, you know, that can't be a manual process. It's something that we need to automate, both in terms of the processing of the DEMs, but then also in terms of how you classify or extract these kind of lake type features. And so that's kind of the ongoing challenges that we're grappling with, is to try and go from what's a kind of an ad hoc case study to something that is kind of scalable and that we could run at large scale.
Well, thank you so much for your explanation. Yeah, it's great. Yeah.
Hello, Matt.
Hi,
Hope
Maya.
hope you recognize this sound, our voice.
Of course.
Yeah, that was very wonderful talk and simplified, nice, explained as usual. Yeah. So yeah, it was very clear and understandable as you explained everything nicely. But I have this question or a comment. Yeah, you can just categorize it the way you want. You showed using that Earth observation dataset, or I think mainly some optical or Sentinel-2 dataset, the water which is going below and then again coming up at after some point. Okay. To understand those things, let's say we are using, as you said, the Earth observation thing. The model, this ice sheet system model or some kind of model will also be useful now to understand those kind of processes. So are we thinking in that direction? Or what is your plan to understand the phenomena using models?
Yeah, no, really good question. So within the study that we've done so far, what the modeling elements that we have used is, I guess, a thermodynamical model. So we wanted to understand the thermal characteristics at the bed of the ice sheet, because we thought that because obviously this is a strange phenomena, and what we could show through thermal modeling is that we expected the bed of the ice sheet surrounding the lake to actually be frozen to the underlying bedrock, and that might have essentially provided the mechanism that allowed sufficient stresses to build up, because the ice was frozen to the bedrock, that then the fracturing occurred and allowed it to propagate up through the surface. Whereas normally these lakes form where you might expect the bed to be at the pressure melting point, so the water can more readily flow out and escape. So within the study that we did, I guess we did some work on the kind of the thermal component. I think you're probably alluding to, an interesting future avenue is to look at how this can inform hydrological models, so models which aim to simulate the flow of water beneath the ice sheet. And that's something that we do want to look at, but I think we feel like we need a larger observational data set before modelers have enough kind of observations to be able to work with and to really understand it. And in the case of the one example that I showed, I guess there's quite a lot of uncertainty in terms of kind of bed conditions and things like that. So ideally, we would have another study first that went and took some field observations out there, produce like a much better data set, which could then be used by the modelers to try and reproduce this event. So that would be one way to go, although we don't have funding to go and carry out field campaigns there yet. And then I think the second way to go would be for us to try and develop a larger observational data set, and then for modelers to work with that data set to see how they could use that to inform kind of hydrological models.
Thank you, Matt.
I think Kritak has raised his hand or he left.
Yes, sir. Am I audible?
Yep.
Yeah. So my question is that currently I'm working Lambert-Emery region. I'm applying IISc. So when I build a mesh, so my problem is that my problem is regarding to the creating the category of, okay, where is the ice is floating and grounding. So the problem I'm facing regarding where the elastic band is there. So because I'm not able to find the sharp transition, I'm finding the transition zone. So using your satellite data, how can we improve that this kind of error if it is there?
Sorry, could you maybe repeat or explain it in a bit more? I don't know. I quite got the exact question, please.
Okay. Am I audible now? Okay. So my
Yeah.
question is that see, I am building a mesh and using thickness and bed data to create the ice floating and grounded ice. So the
Mhm.
problem is that when I'm doing a small change, even a small change, and so the grounding line is quite, it's feeling like a transition zone. It is not showing a sharp line between the like grounding and ice. So if I am using your if I am using any vertical like vertical type of data like satellite data, so how I can get the very sharp kind of transition between the grounding and the floating?
Can I ask which area that you're looking at?
Lambert and Emery.
Okay, because I guess so. I'm not totally familiar with that area, but I guess in some regions you get a very sharp transition where you've got a relatively steep bed topography, but in some regions where the bed topography is relatively shallow or less steep, then you will get, as you say, this kind of grounding zone where you get, say, grounding of an area at low tide, and then it will unground at high tide. And so the fact that you're getting that, and sorry, I'm not quite sure whether you're just producing it from model simulations or whether you're doing it from satellite observations. I'm sorry, I didn't quite catch that.
Okay, I am deriving it from the bed machine data set. So I am using the
Okay.
thickness and
Yeah. So I guess the challenge with the bed machine data is that I guess knowing exactly where it's come from, but I suspect using either altimetry or INSAR data as kind of a complementary source might help to give you some greater either confidence that the bed machine one's correct or just something to compare to. So I think potentially if you're unsure about the quality of the bed machine data, then looking at some alternative Earth observation derived data might be useful there.
okay,
Sorry,
and what can
I'm
be
not sure that helped.
okay, what can be those alternative sources? Because this bed machine data is when I'm trying to even a time of very slight changing. So it's completely making in a kind of a transition zone. I'm not going to see, okay, this is the transition zone. So is there any alternative source which I can use and enhance the result?
So I think there are grounding line data sets out there. So I think probably the most widely available is based on INSAR, so interferometric synthetic aperture radar imaging. I don't know off the top of my head, but I think if you did a search for it, then something might come up, for example, out of Eric Rigneau's group at NASA JPL and stuff. I know they periodically publish them. And so that might already be integrated into bed machine. I don't know, but I guess that would at least allow you to understand whether where they're placing the grounding line is consistent with what you're finding.
Thank you.
So anyone else has any questions, any comments?
Hello. Okay. Think I'm not audible or
You are
hello.
audible, Brahma. You are audible.
Sorry. Okay. Yeah. So, Mal, I had one question. So, given the observations that are required, and given the type of satellites that are being launched and have been launched, for example, SWAT, or you can talk about NISAR, where do you see, we keep on improving maybe the temporal and the spatial resolution, right? But where do you see, or how do you see a game changer emerging in terms of process understanding through these novel and new satellite data?
Good question. So for me, I think the thing we're lacking is that high spatial resolution optical or SAR data. So that's capable of producing the high resolution digital elevation models. So the digital elevation models that I've shown, I think, are immensely powerful and will be in terms of improving process understanding. But all those data sets are derived from commercial providers. So the data are freely available, but the source optical data at that resolution are all from commercial providers. And that presents a barrier, A, to their widespread use, and B, to the kind of large scale operation. So I think the biggest change that could be made would be for national and international agencies, so things like ESA, ISRO, NASA, JAXA, to take on the development and provision of those data in the same way that they provide optical data or SAR data or altimetry data, to actually provide that high resolution photogrammetric data in a sustained and systematic way. I think would go a long way to improving our process-based understanding, because it would mean that source of data was routinely and publicly available, as opposed to reliant upon commercial providers.
Yeah, thanks a lot. Now maybe one question, another one, basically for the benefit of students or researchers listening and researchers. So where do you think is the next breakthrough? I mean, if somebody wants to make a career, let's say, in this direction, what is it that you think, a couple of areas that one should actually actively start learning and actively start probably progressing in terms of research?
So I think, kind of repeating, so I think there's a lot of untapped potential in high resolution digital elevation models. I think at a more technical level, like I think how we combine observations and models, it's something that will develop, I think, quite a bit in the future, in the same way that, say, weather forecasting is quite mature in terms of how they combine observation and models. I don't think we're there at that kind of level yet with kind of data sets relating to ice sheets and stuff, but I think there's a lot of potential there. And then I guess the other one, which is kind of a cliche, but I think it is important, is the whole application of data science, machine learning techniques to satellite data. Like there is so much satellite data out there at the moment, and I don't feel as a community we've quite got to grips with that in terms of how we process and how we utilize that information. And I think some of the kind of the big steps forward over the next 5 to 10 years will be in terms of how we actually better utilize that data at large scale to extract information and insight from it in a way that we just don't have the tools to do currently.
Thanks very much. Praveen, do you have any comments or any questions?
No, nothing. This was a wonderful presentation. Thank you, McMahon. So I think the students here, all the attendees enjoyed very much. Thank you.
You're welcome.
Okay, Mal, then thanks a lot for this presentation. If there are any more questions from audience, students, please, this is last chance probably. Otherwise, you can always write an email to Mal. Okay, appears so. So thank you, Mal, for this nice presentation, and thanks for basically accepting our invitation and giving such an insightful presentation. We look forward to interacting more in the future, maybe sometime. And anytime you're visiting India, let us know. We'd love to have you over personally also to host you here. Local expenses will take care of. to that extent. And if one of us is visiting UK, we'll definitely write to you.
Yeah, well, you'd be very welcome to if you're ever around. So thank you from my side for the invitation. It's been really nice to talk to you today. So thank you for that.
Yeah, thank you all, and till next time. Thank you. Bye-bye.
Bye.
Thank you. Bye.